Hey, Vlad here, DevInsideYou.com. Welcome to another video. Today we're going to talk about programming paradigms, which is something that everyone seems to have their own definition of. Alright, now before we discuss paradigms, allow me to mention something else. Lately I started making YouTube shorts. These are short vertical videos in under 60 seconds. And so for one of them, I asked myself whether I'll be able to explain functional programming in under 60 seconds. I tried and I failed. This video ended up 68 seconds long and I had to speed it up and even apply some pitch correction. As a result, I pissed off a couple of people on Reddit. In fact, this is so common that I call it Tuesday. This is sort of like an unwritten rule of content creation. You can't make an omelet without pissing someone off on Reddit. I'm paraphrasing, of course. I also made a short about monads, and I will show you monads at the end of the video, but it's going to be really fast since I have a full-blown playlist dedicated to monads alone. Also, monads play only a part in functional programming. Functional programming is not all about monads. In general, we're only going to see some code by the end of the video, so enjoy my talking head. Now, this video was inspired by this comment, and I decided to make a full-blown video that goes into depth and explains everything from scratch. And so I sat down to write the script. I rolled up my metaphorical sleeves and I was ready to get my hands dirty and write a lot of code and explain everything into the smallest detail possible. But then I remembered I already have. Story time. It was the winter of 2017 when I decided to create this YouTube channel, and there are many reasons for it, but this is a topic for another video. The content is all about making the world of professional software development accessible to anyone, and also about improving the developer inside you, hence the name. It also mentions that I'm going to use Scala in most of my videos because I love Scala, and also someone on the internet advised me to pick a niche, and so here we are. And so, especially if you're new here, you should probably know that the first 100 videos or so that I made are very sequential and they are divided into several playlists, but not every video made it into a playlist. And since I'm terrible at marketing, you're never going to find a few very specific videos in between of those playlists. But we need to find them because they contain the metaphorical gold. Seriously, I rewatched them before I started writing the script for this video, and the topics discussed in them are insanely crucial to your programming endeavors. So what we're going to do now is I'm going to give you a very quick overview over these 100 videos, and then I'm going to show you how to find these very specific videos that I'm talking about. So if you go to my website, which is DevInsideYou.com, as you probably know, and if you click on courses, you're going to see these cards, and every card has a year label at the bottom right corner, right? So if you go to the bottom, we're going to see the first couple. Okay, so this is the very first one. It's called The Software Run Through Your Veins, and it contains a tiny description. It says, find out if software development is a field for you. It's an entry-level course and no prior knowledge required. If you click over here, you're going to end up at this playlist, and you're going to see that it's, it's very short talking head videos where I basically tell people that, in our industry, you're never going to start learning and what you're getting yourself into, and that, most things are in English and you need to keep reading a lot and things like this. And since I advise the people who watched the first playlist to prepare themselves to never stop learning, I decided to write a tiny plugin for Sublime Text, which was the editor of my choosing at the time, that would connect to your Spotify account and show you the song that you're playing in the status bar at the bottom. The idea was to give an overview over how a full-blown project looks like, and by the end I revealed that I've actually never programmed in Python before. Then the time came to actually teach a first programming language, and of course the language of my choice was Scala. And so I taught Scala from scratch, really from absolute zero, for people who have never ever programmed before. After this, I realized that we need a full-blown project, and we also need to learn about computer sciencey things like algorithmic complexity. And so I created an entire library where we created so-called homegrown Scala collections, just for education purposes, of course. It is this playlist over here, and we're not going to get into it. So let me click on this one, which contains about 25 videos or so. 23, and then I said, what's next, and then we got into the homegrown collection series. And so over here, we're starting with basic things, and we go on to if expressions and functions, and over here, and recursion and types and so on, right? And then over here, somewhere over here, after I explain closures and function currying, between the videos 12 and 13 are the videos that we're looking for. So what we're going to do now is we're actually going to go to my channel, and I'm going to click on videos, and I'm going to sort them by oldest first, right? I'm going to scroll down. I'm going to see this first playlist, then the Python playlist, then a couple of videos in between. And then we see the Scala playlist, again, a couple of videos in between where I needed to explain the binary system, what I needed to explain dependency inversion. And these are the two videos that I'm talking about. These are the videos about the so-called models of computation, and they're inspired by the wonderful book called SICP that I recommended already a bunch of times during my videos. I still consider it to be a Bible of programming, and every programmer should read this book at some point. Probably not at the very beginning because it's kind of harsh. Now, these two videos explain a lot of topics. They explain the substitution model for procedure application. They explain the applicative order evaluation. They explain the normal order evaluation. They explain the environment model of computation. And they even tease the streaming model of computation, which led me to eventually build an entire homegrown collections library just so that I can get to streams at the very end of them, which is somewhere over here. What is a stream, full-blown paradigm, and so on. So for the rest of this video, we're going to talk about paradigms, but if you want details, really consider watching these two videos and maybe like the two videos that are following. In fact, let me actually scroll up so that I can show this to you. Okay, so after these two videos, I'm going into message passing, and also we can skip this one. This was just a fun project, and also into object-oriented value proposition that we're going to discuss today as well. Okay, so if you want details, consider watching this one, and this one, these 4 videos if you want details, or especially if you disagree with something that I'm going to show you. All right, let's finally get to paradigms. This is why we're all here after all. Every now and then you hear people hand-wavily say something like, nobody even knows how to define object orientation. Or you might watch a conference talk where the speaker would say, this is how we're going to define functional programming for this talk to make sense, so that everybody's on the same page. Lucky for you, I'm way more arrogant than that. Story time number 2. For a very long time, I was a big fan of Uncle Bob. And if you don't know who that is, congratulations, you're young. Google is your friend. In any case, for a very long time at the beginning of my career, I religiously believed everything he said. Only after several years, when I gathered my own experience and developed a thing called critical thinking, I started questioning some of his ideas. In fact, at some point I was naive and I even wanted to prove him being wrong about everything. Not publicly, of course, just in my head. And I did with a couple of things. You know, once you get around the block a couple of times, you realize something that seemingly everybody around you seemed to have understood long before you. You know the things that I'm talking about. There are no silver bullets, engineering is all about trade-offs, and you're not a senior developer until the only possible answer that you have to all imaginable questions is, well, it depends. Now, I've been in this industry since 2008, and even after all of these years of my experience, I still believe to this day that the way Uncle Bob defines paradigms is the way to go about it. It is minimalistic, it is very precise, and it's going to make a lot of you disagree. But as my mama used to say, tough shit. All right, I think I warmed you up enough. Are you ready? Paradigms are mental models. A model is a tool that aids in understanding of a topic. A model accomplishes this task by removing details. For instance, you don't need to have a driver's license to understand when you may cross the road. If the light is green, you may walk. If it's red, you may not. You don't need to know when it's going to be green, if it's going to be green, how long is it going to stay green, what shade of green it is. All of these details prevent you, or at least slow you down, from understanding when you may cross the road and when you may not. And so you need to constrain yourself from asking these questions and concentrate solely on the color of the light. Everything else is a distraction. And so, long story short, paradigms are about constraints. Or in other words, a paradigm is a discipline. I couldn't remember where exactly I have this from, but in some of his videos he talks about the very first paradigm, which was imposed upon the size of the source code files, like literally lines of code. If I recall correctly, this discipline was actually imposed upon programmers by their managers. They noticed that if the files were kept short, there were less bugs. The second paradigm, which is way more known than the one that we just discussed, is structured programming. It started with Dijkstra's infamous paper, Go To Considered Harmful. And if you hear people summarize this, it usually goes along the lines of, if you use GoTo, you write spaghetti code is unmaintainable, and so GoTo is considered harmful. Now, what's interesting about this paper is that Dijkstra actually didn't really care about maintainable software. I mean, he did, but this is not what actually caused him to write this paper. He was a scientist, and what he wanted to do is prove, like actually mathematically prove, correctness of programs. And he realized that he couldn't do it if the programmer at any point in time could simply decide to jump to any point in code and never return. This last part, never return, is crucial. What he suggests in this paper is that if we constrain ourselves to always return from our subroutines, then he might actually be getting somewhere with his proof. This gave birth to structured programming, a discipline imposed upon direct transfer of control. When you call a subroutine, you directly transfer control to that subroutine. When it's done, it gives this control back to you. It returns to the caller. By the way, this is something that sometimes gets confused with having only one return statement inside of your functions. This has nothing to do with that. This is about not having go-tos in your language, not having exceptions, not having continuations, unless they're delimited, but let's not get carried away. In fact, since a go-to is simply not present in most modern programming languages, as a modern programmer, you might not even be able to imagine how hard it is. It's almost impossible, actually, to reason about programs which at any point in time can simply jump anywhere else in the entire code base and never return. This is a nightmare. Now let's talk about object orientation, and let me tell you, you're not gonna like this. Object orientation is not about modeling the world. It is not about message passing style. It is not about mutability or imperative programming. It has nothing to do with putting your data and behavior in the same place. It has nothing to do with objects versus primitive types or objects versus data structures. And for sure as hell, it has nothing to do with inheritance. Check this out. Whereas structured programming is a discipline imposed upon direct transfer of control, object orientation is a discipline imposed upon indirect transfer of control, where you use subtype polymorphism to transfer control indirectly instead of using pointers to functions like it was done prior to that in languages like C. Passing pointers to functions around proved to be cumbersome and error-prone, so we decided to constrain ourselves and not to use them anymore. Instead, we decided to use subtype polymorphism, which is a form of ad hoc polymorphism that allowed us to invert the control flow of our applications. As a side note, functional programming languages like Haskell still require a form of ad hoc polymorphism because it's a cornerstone for indirect transfer of control. You won't get far without it in any program that is larger than a simple hello world. However, functional programming languages like Haskell, they don't have subtypes, and so they use something else called type classes. In Scala 2, we can emulate type classes with implicits. In Scala 3, type classes are more built into the language. We have dedicated keywords for them. However, since Scala actually blends object orientation and functional programming, more about this later, the type classes are actually expressed, ironically, via subtype polymorphism. It's a little bit confusing, I know. By the way, I made another short that explains the difference between ad hoc polymorphism and parametric polymorphism, so you might want to check it out if I lost you somewhere there. In a nutshell, ad hoc polymorphism, either subtypes or type classes, allows you to get different behavior based on the shape of a type. Parametric polymorphism, aka generics, allows you to get the same behavior even though the shape of the types is slightly different. Let's finally talk about the functional programming paradigm, which seems to be the hardest one to explain, which is very ironic because it's actually the simplest one. It's just that a lot of people have to unlearn a lot of things to actually understand it. Actually, more story time. My mother told me basic arithmetic when I was a kid. In fact, she did this by playing cards with me. And I wish that I could tell you that I played poker as a kid, but that would be a lie, and we don't do lies over here. In any case, by the time I went to school, I felt very comfortable with numbers. But since the school program cannot assume any prior math knowledge, they start from scratch, and of course from a different angle. And so now I had two mental models in my head about how arithmetic works, the one that my mother taught me and the one that I got taught at school. Neither one was better or worse, but having both of them in my head was confusing as hell, and so my arithmetic skills went down the drain. In short, I had to unlearn one of the models first, and I didn't even know which one was better. Back to functional programming. Structured programming is a discipline imposed upon direct transfer of control. Object-oriented programming is a discipline imposed upon indirect transfer of control. Functional programming is a discipline imposed upon assignment. Now, this is something that needs to be unpacked a little. First of all, there is a difference between initialization, or binding, and the actual assignment, or to be more specific, a reassignment of a new value. Most mainstream languages use the same operator for both of these operations, which is the equal sign that I'm sure you're familiar with. Alright, now if we constrain ourselves to never assign a different value to our variables, two things will happen. Well, actually three. First, we can stop calling them variables because there's nothing to vary anymore. Number two, which is closely tied into one, a binding or an initialization of a new value is always merely an alias for some value. And finally, because of these 2 points, we can use the simplest model for reasoning about our programs. In fact, it is so simple that everybody learns about it in school. No relation to my story. When your teacher says that x equals 5, you can flip over backwards, but nothing in this universe is going to turn this x into something else other than 5. And now, anywhere on the board, at any point in time, which is very important, you can either use the x, which is the alias, or the 5 directly, which is the value. And the behavior of the entire, let's call it program on the whiteboard, is not going to change. And then somehow, when we start learning programming, we get superpowers, and we can turn this x into any other number. And in dynamic programming languages like JavaScript, we can even change its type. Now, all of a sudden, you need to be very careful, because you cannot just assume that at any point in time, you can replace x with its value, and the results will stay the same. Most likely, they won't. By the way, you might need a little help to understand that last point. For example, in Scala, since the very beginning, we're told never to use vars. However, you can, even if you use a val, you can still assign something like an array to that val. An array is mutable, so it takes a little bit of finesse to understand that there is still assignment somewhere inside of this array. Even if it's turtles all the way down and you assign a new value to the same place in actual hardware memory, there's still assignment. You could even hand-wavily say that programming without assignment is expression or value-oriented programming, even though the actual computer science term for it is the substitution model for procedure application. And by the same token, you could say that programming with assignment, aka side effects, can be called location or place-oriented programming, even though the computer science term for it is the environment model for procedure application. Again, if you want more details about these things, watch the videos that I mentioned before. Now, most people find it challenging to visualize how to perform side effects in a functional program. And the trick is that whenever we have a piece of code which would use assignment or produces a side effect, we simply wrap it in thunks. A thunk is a function that doesn't require any arguments. And so we don't have to deal with side effects. We simply deal with functions that, when run, will produce side effects. And the trick is that we never run those functions. We simply compose them all together. And by the way, we use monads for that. And by the end, the entire program, no matter how big, is just one gigantic function. We give it to our runtime, and the runtime simply calls it. In languages like Haskell, the runtime is built into the language. In languages like Scala, well, you have to call this function yourself. Or you can use a functional library that will wrap it nicely for you, and it will also call it for you eventually. In any case, this is the only place where we cheat and break the substitution model, and we call this place very dramatically the end of the world, or the main method. Now, I'm almost ready to show you a little bit of code, and it's actually exactly the same code that I've shown you in the shorts. But before we go there, allow me to mention a couple more things. All of this talk about paradigms and constraints is not there just to sound cool. It's not there so you can use it to show off to your colleagues how smart you are. The reason they exist, and also the reason why some people never seem to be able to shut up about them, is because they're useful as hell. Code bases that are constrained by all of these 3 paradigms are a freaking utopia. Unfortunately, most of us have never seen beautiful code bases like this. And so, as a senior developer, you might have this urge to throw your hands in the air and claim that there is a trade-off. And yes, most of the time, there is a trade-off. But there are so few things in our industry that are an easy trade-off to make. And trust me when I say this, paradigms is one of them. Which brings me to my next point. A paradigm is a discipline imposed upon your programs, or to be more precise, upon you, the programmer, and not on the programming language that you're using. Our programming languages are just tools, and they're trying really hard to encourage you to do the right thing. But they're not bulletproof. This is also one of the reasons why you're being paid so well. Do you consider it to be professional to claim something like, oh, the compiler did it, or, oh, even if we had tests, they wouldn't have caught it, or, oh, IntelliJ formatted it like this? I suggest that instead we take ownership of our craft. The compiler didn't do it. I did. I didn't write that test, and I allowed IntelliJ to format the code like this. If you know who Jocko Willink is, he has this slogan, discipline equals freedom, and it definitely applies here. And so saying things like, even Haskell has exceptions, and it is therefore not a pure functional programming language, is meaningless, because applying paradigm labels to languages is meaningless. Now, it is still useful in making the trade-off whether to use it or not, but it is not useful to define the language. We only have languages that try as hard as they can to constrain your programs to help you stay disciplined. But ultimately, I'm sorry to tell you this, but it's all on you, which is also one of the reasons why I created this channel, to help you improve the developer inside you and me. In fact, I just remember there was a meme or even a t-shirt back in the day saying something like, my language has more paradigms than yours. What does this even mean? Does it constrain my programs more? Does it remove more language features like other languages do? For instance, it's going to be very tricky to program in a non-functional way if you actually remove assignment from the language. All of a sudden, your while loops will also need to be removed. All of a sudden, your if statements will have to become expressions. And even though technically there still can be assignment hidden somewhere inside of print lines or arrays, the code base that is written in a language that doesn't even have assignment is going to be pretty functional. I'm sorry to tell you this, but Scala is not a blend of object orientation and functional programming. It is a pure object-oriented language at best because it permits assignment. Sure, it encourages you to program in a functional style, but technically it's not functional. And even more technically, as already mentioned, it is very meaningless to apply paradigm labels to languages anyway. So let's just not do it. By the way, functional programs have this stigma around them of being slower, and it is partially attributed to the fact that our tools cannot enforce this discipline, and therefore they are afraid to apply optimizations to our code base because they're afraid to break the semantics of your program. If we keep constraining ourselves to program without assignment, then maybe one day we're going to live in a world where we will be able to tell our entire toolchain that we're programming without assignment. I'm talking, the Scala compiler, the JVM, Docker, your operating system, your CPU, and maybe, just maybe, the optimizations that they will be able to apply will be freaking crazy. And so one of the big reasons why functional programs seem to be slower is because it's not a fair comparison. We need to level the battlefield a little bit. In fact, back in the day, there was a thing called a list machine. Google that. All right, let's look at a little bit of code and wrap this up. I'm not going to type anything like I usually do from scratch because this video is already getting kind of long, and I just want to show you a couple of things. So what we're seeing over here is exactly the same program. On the left, it is written in a regular non-functional style. On the right, it is written in a functional way. And as you can see, it's very, very similar. So I'm going to run it real quick. So it's going to be not FP, this one. Okay, let me create a little bit more space. All right, so what you see inside of here is basically two programs, this one and this one. On this one, in this one, the value of this expression is substituted for its alias, right? So they should behave the same, but they don't, which means we're breaking the substitution model. The first program prints it out only once. In fact, it's actually printed out over here because this is a val. So you need to take care whether it's a val or a def or a lazy val and so on. Over here, nothing is happening because this unit, this effect already happened. Whereas over here, it didn't happen yet, and therefore it happens twice. On the right side, pretty much exactly the same thing. It's just that we're wrapping this side effect into a thunk, which is just a function, doesn't have any arguments, but it produces, but it's side effects when we run it, but we never run it. Let me run the app over here. So this is going to be FP. Over here, we're starting with printing out these hyphens, okay? Then we have the hyphens again, and then we have the first program. So the first program is kind of like between these two lines. And we have the second program, which is between these two lines, and as you can see, they behave exactly the same because nothing was printed out, because as I already mentioned, we actually never run our thunks. We just keep composing them at the very end, right? So this is all of them composed into one. Usually we would use monads for that, and I'm going to show you how to use monads in just a second. But the point is that we keep composing them, okay? So until here, still nothing happened. So we're seeing the print lines only at the end of the world when we're actually evaluating this one last thunk, this one last function. So the only output that we're seeing is between the last two hyphen lines over here. And so when we're substituting the alias with its value, the program still behaves the same. In fact, we don't even need to care whether this thing is a val or a def or even a lazy val. It doesn't matter much anymore. There are still some, slightly different performance characteristics, but the meaning of the program stays the same. Let me change it back to a val. Now, this is actually all that I wanted to show you today, but since I already made this tiny short about monads and 25% of the people didn't really like it, I'm going to run you through monads real quick. It's going to be really fast, and you're probably not going to understand it if this is the first time you're looking into this, but I have a full-blown playlist about monads, so you can look into that. All right? So let me go to monads real quick. So this is exactly the same code as we have seen in the shorts. I changed only one teeny tiny thing, which is a Scala syntactic thing. Okay, so we have regular functions over here. This is just a type alias. This is just a regular function from A to B, and you can always compose like any two functions. You can always compose them with this code. You just produce another function, right, that starts with an A. You stick it in the first one, so B comes out. You stick the B into the second one, so C comes out, and then you're done. So you have a function that goes from A to C. Now, if you're dealing with these special kinds of functions that are called classly functions or classly arrows, because they were worked on by a guy called Heinrich Classly, who was a Swiss or Swedish mathematician. I don't remember. I have to look this up. Right. So they're just named after him. So these are the functions that don't just go from A to B. They go from A to B that is sort of wrapped into some D. Some people call it context. It doesn't really matter. But it's always in something, right? So this could be an option. This could be a list. This could be an IO. Whatever. Now, if you want to try to write exactly the same code, that given like these two functions, we're going to try to compose them, you're not going to be able to do this. Okay, so we have these special kinds of functions now, right? So they always return a B that is wrapped in a D. They always return a C that is wrapped in a D. And we need to return a C here, over here, that is again wrapped in a D. If we don't know anything about the D, then after we're creating a function that goes from A to D of C. Okay, so what can we do? We stick the A into this first function, D of B comes out, and then we're stuck. Because we don't know anything about the D, we have no idea how to rip out this B. And because we don't know how to do this, we cannot stick it into the next function. So we need to have a little bit more information about this D. And this information comes from a monad, which in a language like Scala is just an interface. The difference is that this interface is going to be defined for some specific D. It's not defined for all kinds of Ds. It is defined for some D, right? So a bit more down over here, we're going to define a monad for when our D is hard-coded to be an option. Okay, because it knows how an option looks like, it knows how to rip out the B, and therefore it can stick it into the second function. And so now that we have all the pieces in place, we have two functions like this, we can compose them together by using a monad that the compiler will inject for us. Okay, we don't need to write this code, the compiler will do this for us. The only thing that I changed from that other video is this tiny thing, right? So this is a Scala 3 thing that will allow you to call flat map with two different syntaxes. Like this is the sort of like the data-oriented, the functional syntax, where you say monad dot flat map, and then you give it these two things, this one and this one. But you will also be able to just not use them, and just sort of like have this monad in scope and just do db dot flat map and then just give it bdc. Okay, so this is a little bit shorter. This is a little bit more. It feels a little bit more object oriented, and this is what this syntax is doing. And I did this to show you how to write this program together with monads. I can leave it or I can revert this. It doesn't really matter. I have fp with monads. Okay, it's exactly the same program, right? So until hold up, until over here, nothing changed. Okay, it's just that before, when I cannot collapse this because of fancy syntax. So before this program, let me actually show this to you. Okay, so we were calling all of these four functions inside of another function, right? So this is how we compose them. We sort of did it manually. Over here, what I did is first I did this, right? And then I did this, and then over here, I pressed enter like this, and I did that like this. Then I went over here and I said val, and we don't care about the value that is produced, right? Because the value that is produced is a unit. Now, all of this code still compiles, okay? So if it didn't compile, we would see an error message like this, okay? So everything still compiles. So I did this, okay? And then I went over here and I wrote it down, right? So this is like in the Scala 3 syntax, so we don't need the curly braces. This is still how you can do this manually. And with all the pieces in place, we use for comprehensions, and the program basically becomes, it sort of looks exactly the same. Like this thing traveled down over here, vals disappeared. We still have the underscores because we don't, like, usually you would take something from here and stick it into the B, but in this case we don't really need to do this. Okay, and the equal symbols, they turn into these arrows, right? And behind the scenes, we don't use this function, right? We don't compose functions unless we're writing programs in a point-free style, but we usually don't. So we just go and we use flat maps directly. So we're not dealing with functions. We're already dealing with these things, which are already D of something, right? So over here, for example, an A, it's a D of something, right? So our D is a thunk, right? So our A is a thunk of unit. B is a thunk of unit, right? So we have this thing we just call flat map on it. So this is what we have over here, right? So you can either do it like this, you just nest them, a flat map and then the same underscore, and you would usually be able to stick into the, use it together with a B and X and Y, but we don't use them, so we can use the underscores, okay? And I also did this, I'm gonna say something about this in just a second. Or you can do it the other way, right? Because monads are associative, which means you can have like the left association or the right association. I believe I marked this correctly. I believe this one is the right one and this one is the left one, okay? But usually you would write, you would write the code with 4 comprehensions, right? So behind the scenes, this code desugars to this one. In fact, you would write it shorter. In fact, let me actually run this. FP with monads. Let's actually put this thing on the right like this, okay? So somewhere at the bottom, right? So we're running the first one, we can run the second one, we can run the third one. They're all the same. So if you're running the fourth one, for example, if you're not using the 4 comprehension, you actually don't need this last one. It's going to behave exactly the same. And the third one, exactly the same thing. You don't need this last map, okay? You can just remove it. But with 4 comprehensions, they actually need a map. I'm sorry, over here, this yield is being desugared into a map. This is why I cheated a little bit. And so first of all, I defined a monad for composing a monad for composing functions, for composing thunks, right? Over there, we had a monad for options, which look like this. And over here, we have a monad for thunks. Usually, thunks are called I/O, right? So this is the I/O monad. That is like stack safe, by the way, but this is for educational reasons, so we don't really care. But the 4 comprehension wouldn't really work without me and go and defining map as well. So I also defined an extension for thunks instead of going through functors and all of these things. As I already mentioned, I don't want to confuse you with monads, right? You can get into monads a bit later. The whole point of functional programming is a substitution model for procedure application. All right, I'm talking too much at this point. I hope that I didn't make any keyboard warriors angry, and I see you in the next one. As always, it's been Vlad, DevInsideYou.com. Don't forget to like this video if you did, subscribe if you want to improve the developer inside you, and if you learned something today, consider supporting me on Patreon or on GitHub sponsors, whatever you prefer, and just watch my videos weeks and sometimes even months before everyone else. And most importantly, take care.